Morning.
Good morning.
We are going to talk about that important section that I talk about it. We give you the notion of sequences. Now we're going to get through that method of mathematical induction. Okay. Let's see how far we can go. It's a very standard method, but we don't like to go to the formula right away. I want to give you the motivation of how we're going to arrive at this interesting method, and then we are going to do it. So basically, mathematical induction is going to be used in different formats. This format that we're going to use it in order to prove some theorems. So basically, if you be given a situation, okay, that involves of proving a fact, a property about the mathematical structure, depends on a number n, or a counting number n, if you like. So you have an equation. You want to prove that this equation is true for all natural number n. You have an inequality. You want to prove that this is true for all natural n. So basically, those actions that we're going to do is like a function. We call it a sequence of operations, if you like. That sequence of operations is denoted by Pn. Then the procedure is going to be that in order to prove your case, you have something that we call it the basic step. It's like if you want to build a building, you need a foundation. So you have to prove that your foundation is firm. So you have to prove that whatever you want to prove, the equation inequality, is true for the basic value of the given number. Then, based on the foundation, you are going to go up. You go to the first floor to see what's going on. So the first floor means the first action, the basic number. If your basic value starts with the 1, so you have to prove that this procedure is true for 1. So as soon as you prove it for 1, you get the foundation, you go to the first floor. You got the first floor. So you are going to try to see from whatever you did to the first floor, to get the first floor, repeat it again so that you'll be able to get to the second floor. So when you get to the second floor, you have very much got some experience. So what you can do is, you can do whatever you do to the, how did you go from the first to 2? You are going to build up so that you can from the second one to the third one. And then you can continue forever. You say that this operation is going on inductively or recursively. So you can go on forever, or you get to the stage that you say, oh, I've done it for 50 floors, if you like. So from now on, it's going to be the same. So if you give me one step, then I can go to this next step. This type of procedure that we're going to use as a mathematical induction. So it's recovering something from the previous action, previous repeated model, if you like, and that's going to be the case. So what we are going to do, we are going to use common sense, if you like, to build up that structure. Okay, the common sense is, you know that if you want to change money, that's the best example to start with. If you want to change money today, you can change it to what? You can change it to the pennies, okay, dimes, nickels, and quarters. For the long time, people have been asking that, we can collect all these coins, so we can reduce it to just a couple of them. Okay, so the question is, can you do it? If I give you something like $100, $40, can you change it for me if I ask you to do it only using, let's say, new coins? Your new coins are going to be something like 3 cents and 5 cents. So that's one of those questions that we've been thinking about it around to be able to change our system. So what I'm going to do, I'm going to propose such a question, and we try to use common sense to solve this problem. If you like it, or if you can do it, so that you can put it in the format of a mathematical procedure, and then we go for this one, okay? So the idea is going to be called mathematical induction. Then I give you the history from different point of view. But I like this method, and I find it very useful for the people to understand it. And you are going to repeat this procedure for us for some abstract problems, okay? So what is mathematical induction? Or just simply induction? Okay, so we start with this question that I talk about it, okay? So let's have this question. You'll be given one of these problems in your next test, and you have some in your book. So what is the question? The question is, we would like to form a new system, okay? So this is our proposal. We propose that I can form, let's say, forming, if you like, forming any amount, any cent amounts, okay, whatever you give me, $12, $14, etc. By using, not the usual practice, by using, okay, suggestion is, how about 3 cents? Okay, 3 cents and 5 cents only, okay? 5-cent coins. You can do it with others, you know. And the problem that you have, we change it. So that's a question. So what does it mean mathematically? This question, you know, this is in word form. Change it to the abstract form so that we be able to build up something about it. So we can just elaborate it, this question. We say, oh, so mathematically this means, so the question is, okay, so the question that you're proposing is going to be is mathematically it's for, okay, it's going to be for all integers, n is going to be the number of the cents. You must have at least 8, okay, this is it, 8 cents. For all integers n greater than or equal to 8, you want to show that this can be written as a combination of 3 and 5. So combination of 3, 5 is for all n greater than or equal to 8 cents or n cents, with those restriction. N cent can be obtained. Okay, can be obtained using 3 cents. Okay, 3 cents and 5 cents coins. So no question is better. Okay, so what does it mean again algebraically? Let's say equivalently. Okay, equivalent, this means 8 is going to be a combination of multiples of 3 and 5. So this means I can prove that there is an A, okay, and there is a B. There is a A and a B such that n is equal to what? N is equal to the 3A plus 5B. You see, this is algebraic format, if you like. Okay, any question? Everybody happy about the question? This is it. We have n cents. We want to change it into 3s and the 5s. So mathematically, this means your n would be a combination of this multiple. Now, what we are going to do, we are going to again make it better. Okay, in order to make it better, we can bring a predicate, if you like, or a sequence. So again, I elaborate this question as if what? If I assume that the Pn, okay, the predicate or the sequence. So Pn would be this expression. Pn is the fact that the n cents, okay, n cents can be obtained. Okay, n cents can be obtained using 3 cents, okay, 3 cents and 5 cents. I write it down in a format that I'm eventually call it mathematical induction. Okay, so this predicate Pn. So what I should prove this, you see, I should prove this one. So one should prove, or I should prove, you should prove, one should prove one should prove that this Pn, you see Pn, the expression, the predicate that you talk about it, Pn is true. Okay, Pn is true. Pn is true for all n greater than or equal to 8. You see, nice. We change it into this format. So that's now we know the question what it is. Okay, n of course is less than 8. The least number that you have is 8. So when we say p of 8 means, you know, p of 8 means this expression is true for n equal to 8. Okay, p of 10 means it's true for n equal to 10. Okay, any question? So this is what we have to prove. We have to prove that for all integer n, okay, positive integers, Pn is true. So let's write a couple of them to see what's going on. Then they get the idea to be able to do everything in total. Let's try a couple of special cases. Then that will give us. So I'm going to have a chart here. Okay, in this chart, I am going to have, I put the number of in this case, I put the number of amount of cent. Okay, number cents or amount of cents. So these are going to be my cents. And then this is how I'm going to break it. I'm going to break it for you into what? I'm going to break it into the to the combination of 3 and 5 zeros. So this is how I'm going to show that how to obtain. Okay, how to obtain it, if you like. Obtain it with those property that we talk about all this stuff. Okay, everybody happy about question? So let's start with the basic one. If I give you 8 cents, how are we going to write it down as a combination of 3 and 5, or 3 cents and the 5 cents? Any suggestion?
One of each.
One of each. Very
3 in the.
Okay, this is it. So we are done with the basic one when n is 8. Now we get a couple of them to see how we can, how we can arrange it. If we go with the 9 cent. Okay, any suggestion for this one?
3 threes.
3 threes, very good. That give you 3 threes. Just think about this one, look at this one. So in order to get the 9, we have to add the 1 to this combination. Okay, if you add the 1 to this combination, you have a 5 here. So that 1, you can join the 1 to the 5, make it to the 6. Then that gives you 3, 3. Okay, let's see if it's coincidence or it can be done again. So if you go to the 10 cents, any suggestion for this one?
2 5s.
2 5s. 2 5s. Okay, let's see how we can get it from here. We already got the 3 threes here. So if we have an extra cent, that extra cent and these 3 would make it into the 10, and 10 would be 5 5. Okay, so we go to the 11 to get the idea, then we can extend it. 11. Okay, 11. Any suggestion for this one?
A 5 and 2 threes.
That's it. 5 and 2 threes. And we check to see how we get it. You see, this is a 5 and 5. So that extra one, we can add it to 1 5 because we get a 5 here. Then make it to the 3 3. So we see if you have at least 1 5, that can be done. Because that 5 and the 1 extra would be 6, and already the rest are on those formats. Okay, and then we'll be able to do it. And we can get one more to get the idea, then extend it. 12?
4 threes.
4 threes. Okay, that gives you 4 threes. That gives us 4 threes. And if you want to get it from here, again, since you have a 5 here, you add 1 to the 5, then we get those threes, and then we can see it really right away. So we have a 13 here. Okay, any suggestion for the 13?
2
2
5s, 1
5s
3.
and a 3.
2, 5, and a 3. 2, 5, and the 3. So that should give us an idea that if you just have, if you can assume that, you got it up to the one step, you should be able to recover the next step right away, okay? And now we got the idea that it's important to look to see what would happen in the previous part. In the previous part, if you have at least 1 5, if you have 1 5, you can add the 1 to get the 3 3. If you don't have any 5, you must have at least 3 3s because you start with at least 8 cents here, okay? So that 3 3, you can add the 1, make it to the 10. So that give you an idea to do it for any number that's given to us, okay? So we can check to see what we did so far. What we did so far means you just give me any amount, I can do it. Because as we go on, we can do it. So we can, at this level, we are going to suppose that, okay? Because we can do it. So we fix it. We say, suppose that you give me, suppose the number k greater than or equal to the 8 integer. Okay, suppose k is greater than or equal to, is an integer, is a given integer. Okay, you give me what? A given integer. Given integer, okay, such that pk is true. pk is true. Remember the pk is that you can get those combination. So pk is true means, then what does it mean? This means k is a combination of 3 and 5s. So then this means there is a A and there is a B. There is a and there is a B such that the k is equal to the 3a plus 5b. Okay, so you fix it. You fix it. So what we are going to do is we are going to show you that if you give me the k, now I can make k plus 1 for you. Okay, then I can do it all the time. So I've already proved the theorem. So what now we can do is we say, oh, I can, or one can show. Okay, one can show that if you give me one more cent, k plus 1. Okay, k plus 1 cent can also be, can also be obtained. Okay, obtained using what? Using the 3 cents and the 5 cents. 5 cents coin. Okay, so this is the one that we are going to prove it for you. Now, so you have this, okay, you have this. Now you have to prove that for k plus 1 is going to be the same thing. You must get back to see what you did in this case. You see, as you can see, in the previous one, the point was whether in the given combination you have the 5s or you don't have the 5s. Because if you have at least 5, you add this 1 unit to the 5, then we get a 3 3. If you don't have any 5, you should have at least 3 3s. Then you can do it. So we have to break the problem in 2 cases to prove this. So the red one is the one that you want to prove. So we are going to consider the case 1. What's the case 1? Because you want to prove that there is another A and a B, such that k plus 1 is going to be again 3a plus 3b. Okay, 3a1 plus 5b1. This is what you want to prove. So the case 1 would be, you suppose that the b is greater than or equal to 1. B is greater than or equal to 1. This means you have at least 1 5. You see, this is a situation they're going to have. Suppose this is the k amount, okay, the k cents. And this k cents, whatever you have, but you know that at least you have 1 5. You see, you have a 1 5. Okay, you know that the k is a combination of 3 and 5. So if you have at least 1 5, okay, I'll call this 1 5. There are some others, but you don't care. You just pick this 1 5. So what we are going to do is we go, and when we have that extra cent, okay, if you get an extra cent to make it into the k plus 1, so the situation that we're going to have is going to be this one. So you have the 5, so what you're going to do, you are going to add that 1 unit to the 5. And you change the 5 into the 6, and the 6 would be 3 and 3. So what we did in this case, we change it to the 3 and 3. Everything else is already nice, okay, to get there. So that would give us a k plus 1 that we are going to be interested in to get these numbers. But this is, you have to show it mathematically. Now we use the fact mathematically. And so what we did, you see, you suppose that now mathematics. So we say, oh, suppose, because the k was given to us, okay? Suppose b is bigger than or equal to 1, and k is equal to the 3a plus, okay, 3a plus 5. Now you want to make k plus 1 as we did it over here. So what is going to be the conclusion? Then bring the k plus 1. So this is going to be k plus 1 equal to the 3a plus 5b plus 1. Okay, now you have to show that this is a combination of a and the b. Again, exactly how you did what we did over here. We borrow 5. We borrow 1, 5, so that this 1 and 5 would be 6. So borrow. How are we going to borrow it? So this is going to be a 3a. Okay, this is going to be 3a. And this is going to be a 5b. You borrow 1, 5. Okay, you borrow 1, 5. So at the same time, you have to give it back. Okay, you have to give it back, whatever you borrowed. Okay, that's going to be the one. The one that you borrow, that make it to the 3 and 3 that you like it. Okay, and then you have to take care of the rest. So what you're going to have, this is going to be a 3a. Okay, it's going to be 3b. And this is the way we write that. This is going to be a 5b minus 5 and the 6. Okay, now they put the 6 and the 3's together. So it's going to be 3a plus 6. Okay, and you have a 5b plus 5 minus 5. Remember, you want to show that they are combination of 3's. So we can factor out the 3 here. So that give a plus 2, and we cannot factor out the 5 here. Make it to the 5 minus 1. There you are. You call this one A1, and you call this one B1. So what you have? You prove that this is going to be a 3A1 plus 5B1. Okay, so that's it. So you show that if you give me the K, if I know that the K is a combination of A and the B, 3 cents and the 5 cents, I can prove it for you that the K plus 1 would have the same property over here. That was the case when you have at least 1, 5. Any question? We are not done. We have to consider one more case, okay, to show that, yes, we can do it for you. So if you give me K, I give you K plus 1. So I can repeat this one over and over and over. So eventually I proved it for any n. Okay, so let's consider the case 2. For these numbers are always the case. You have to go with this type of procedure. So the case 2. The case 2 is, remember that was the one that you don't have any 5s. So the case 2, you have to suppose that there is no 5s. Means the b is 0. If b is going to be 0, so your k is just a multiple of 3. Okay, like a 3a if you like. Okay, and this is the one, remember, at least we are going to have 3 3's. I'll just show you again. So this is going to be the case that we have. So we have a 3 3's here. 1, 2, 3, 1, 2, 3, 1, 2, 3. And of course, there are some others. Okay. So in this situation we're going to have, so we have 3 3's. And this is our k cents. Now add that 1 cent again. And we'll talk about it. We add this 1 cent to those 3 3, make it into the, okay, make it to the 10. So that was 1, 2, 3, 1, 2, 3. Okay, and you have one here. So that's what make it to the 10. So the 10 would be a 5 and the 5. So, and that would give us the result that there. And this is going to be your k plus 1. Okay, so in this case, idea is you have to borrow 3 cents, 3 cents, and you add the 1 to do it. So mathematically, this means you have to do it mathematically. So we say, okay, suppose k is equal to the 3a. Okay, so bring the k plus 1. So the k plus 1 would be 3a plus 1. So in order to match the 1, you have to borrow 3 3s. You need a 9. Okay, so it's going to be 3a minus 9 plus 9 plus 1. That 9 and a 1 would be 10. That we talk about is going to be 3a minus 9. And this is going to be 10. Okay, you are looking for the 3 and 5. You have it. You factor out the 3 here. That give you a minus 3. And you break the 10 into what? Into the 5 times 2. Okay, so that's it. You call this one A1. And you call this is B1. So you arrive at the 3A1 plus 5B1 again, which is k plus 1. Okay, so in both cases, it's possible. It's possible that if you give me k combination, I can make it k plus 1 for you. Okay, so this can be done for any, okay, any mixed number if you like, any fixed number. So eventually what we proved is just a model of the mathematical induction. So let's see what we proved. You see, so this is what we did. Note that we proved. Okay, we proved that. What we proved that the basic step, you see part 1. We proved that the idea is true for the basic number, for basic value of n. Remember, the least number of n was 8. So we proved that P8 is true. This is going to refer to it, usually denoted by B, and we call it basic step. Basic step of our argument. Because you want to prove it is true for all natural number n. Okay, that n would have a restriction. If you don't have any restriction, n start with the 1. Okay, and the second part, what we did in the second part. In the second part, we assume that if you give me a k, you see, if k greater than or equal to the 8, any integer is given, okay, is given such that pk is true, means the property is true, you assume it's true, then you prove it. Then we prove that pk plus 1 is also true. Pk plus 1 is also true. It's like the building that I talk about it, you see. If you go to the 10th floor, then you can get to the 11th one. You go to the 11, then you get the 12. And so what we did, the conclusion of these two, you see, the conclusion of these two is the fact that therefore Pn is true. Pn is true means this identity is going to be true for all natural m, okay, for all n greater than or equal to the 8. This procedure is going to be called mathematical induction, okay? We call it the mathematical induction principle or just a mathematical induction method in order to prove the, okay, any property of the n. So I'm going to write it down officially. Very nice example, this one. Okay, out of this, you know, we are going to go to some abstract term for the rest of this chapter, okay, to talk about it. But this is a very good procedure you have to keep in mind from now on, that you are going to okay, work through this chapter, if you like. So any question? Let me write it down. Yes.
Yeah, I'm just kind of confused. So was this all the way to prove the original statement, 4 cent amounts by using 3 cents and 5 coins, or was it?
Yeah. The idea was if I give you n amount of cents, okay, and for any n, you should prove that you can change that one amount to a 3 and 5 cents. So that was the question. Okay.
So the whole process would be to multiple cases.
Yeah. But you have to finish it generally. Okay. This would be, we will make it short. That idea is. So the procedure is, you see, Pn is a property, is a sequence. It's a sequence that's given to, is a predicate. Is a predicate that's given to, it depends on n. Okay. You are going to define the Pn. In this case, the Pn was what? Pn means n can be written as a combination of 3 and 5. In other problem, Pn can be anything else. So you have to form this Pn first, or the Pn would be given to you. So you want to prove that for any integer, greater than or equal to the 8, that integer can be written as a combination of 3 and 5. So we change it, we say that this is going to be n cents. So for any n cents, if I give a bill of the n cents or n dollars, you should be able, to change it for me into the 3 and the 5. So that's the idea. Okay, the Pn, you have to define it, or it would be given to you. This is one of our difficulty. On the test, the people, they don't give me any Pn. They go with this procedure. I put a question mark for them, I don't give you any point. So you have to express the problem. So what I did, you see, look at the one that we did again. You see the problem of the way I form the problem. You see, the way this is very important part of the problem. You have to create a predicate. So the question was, this is the question. The question is, can you change any amount of the cent that I give you into 3 and the 5? So mathematically, this means if I give you a number greater than or equal to the 8, can you write it down as a combination of 3 and 5? So that's the question. So we change it to the predicate form. You need in this predicate. When you change it to this predicate, you have 2 steps to prove. Step 1 is you have to prove this is true for the basic step. You see the basic step, the basic value of the n. So that's step 1. We call it basic step, P of 8. P of 8 can easily seen that it's going to be 3 plus 8. Then you,
Sorry,
yes.
it's only 8 for specific.
No, write it on the chat because I cannot hear you. Okay, your voice is 8 would be given to you because you cannot do it if you don't have the 8 cent. You cannot do it with the foresight. The basic part must be, okay, can be done. You see, this would be given to you. So the amount of the value, the amount of the money that you can do this problem with it is going to be 8 cents, okay, or the 9 cents. So this basic one would be given to you, okay? If it's not going to be given, is n bigger than or equal to the 1 to get these numbers, okay? Yeah, 8 is a specific for this problem. Yes, of course. Yes, depends on the problem. Depend on the problem, if you want to treat with other coins. So that basic would be given, yeah. Yeah, you read the problem, you see it. So prove the following identity for all n greater than or equal to 1. Then you know that the basic one is 1. Okay, there is always a basic number. So we check the basic first, okay, for the P1. Then you see the next step was you suppose that you can do it. You suppose that you can do it for a fixed number K, 100, 2000. You assume that you are able to do it. You already done it, if you like. You assume that it is true for K. You prove that it can be done also for K plus 1. So you assume one step and you use that step to be able to do the next one. If you can do it for K, then K plus 1, this means If you can do it for 100, you can do it for 101. You can do it for 101, so you should be able to do it for 102. So you did for 102, you should do it for 103. So this would follows the fact that if you prove this part, then you can assume that it can be done all the time. Okay, so that would give us an idea. We haven't gone through this officially, of course, but that gives us an idea that how we are going to organize this number. Okay, how will we know what to choose as our cases? Oh, it depends on the problem. And you know, it's a money problem. You know, we have lots of the money is nice, so you have to do a couple of the parts as I did to find out how we're going to get it from when you change the money, if you want to stay with this problem. Okay, but otherwise the rest are mathematics. Okay, and this is mathematics. You see the numbers that I take out for the money, you will see it, that it depends on the nature of the problem. We will get it. I'm going to show you how to do it. But with this one, we just want to get the feeling that how this procedure is working. Okay, what is the steps that we have to prove? So the step that we have to prove, we should always prove that it's true for basic step. And some people ignore this one, but I give you many examples that the property is true for the basic step, but it's not true for the rest. Okay, so you have to prove the basic step, then you fix it. You suppose the PK is true, but you have to use some tricks, theorems, definitions to get it to PK plus 1. Then you can say, oh, so by mathematical induction procedure, this Pn is true for all the time. You see, this mathematical format was given by a guy. His name is Piano. If you check on internet, you see quite a lot about him. He was the guy who just kind of introduced the system of the natural numbers, which is counting numbers that use. So the counting numbers, you know, it's going to be 1, 2, 3, 4, 5, 6. But the way he used it at the beginning was this fact that we assume that, you see, he wanted to create so-called the natural number set. He assumed that there is one element, you see, he said, I introduced a set n for you, a set n for you, with the following property that is, I assume that 1 is in n. 1 is in n. That's basic step. Okay, he assumed that 1 is in n. Then the second step was, if n is in n, then n plus 1 is also in n. You see? So 1 is in n. So 1 is in n. So 1 plus 1 must be in n. 1 plus 1 would be 2. So 2 is in n. Then you come back. Since 2 is in n, 2 plus 1, 3 is in n. So this is how you get these numbers right away. You know, any number would have something after it, if you like. Then his conclusion was this set is unique. Unique means if there is any other sets that would satisfy this condition, any other sets that would satisfy this condition that the P1 is true, and if PK is true, then PK plus 1 is also true, that set must be the set of counting numbers. So that's why we said the Pn is true for all numbers n, because there is only a unique set that would satisfy this condition, and that set is the set of natural numbers. And you know, you can see it for yourself. It's not easy, you know. It took mathematicians. They have different schools, methods to argue about it, but we're just using that idea, that fact. Okay. Any question? Let me write down officially. I didn't write. These are all motivation of this subject, and this is a great method for proof in mathematics. And we change it later on a little bit, and you use it quite a lot. Okay. Your proof is the only method that mostly you prove in your, you know, your advanced level, if you like. So officially, we are going to use this fact. We get it as a fact, as a principle, as a theorem. Okay, we call it, okay, a principle of mathematical induction. not a proof. It's something that we believe it. Mathematical induction. So this is, we use it as a method. So there you are. As I did, suppose you have to have something. Okay, suppose Pn, whatever it is, Pn is a property. Pn is a property that is defined. Okay, that's this defined for integer n. It's going to be, positive integer. And a fixed number, okay? And a, if you like, is a fixed number. That fixed number is that a starting point. That should be given. A fixed integer. Okay, so Pn, whatever it is. Pn, whatever it is, a property is a property. It depends on n. A is a fixed number. Now we assume the following is true. You see, that's the case. Suppose the following true statements following two statements are true. First one, we call it basic step, denoted by B, so that you know that. Basic step is this idea, this property is true for the basic value. Basic value is that A that would be given to you. Okay, so this is it. P of A, it's mostly 1, and sometimes different, like the 8 that you saw it. PA is true. Okay, PA is true. This is called basic step. Basic step. Okay, what's going to be the next part? The next part is called inductive step, I. What is inductive space? You fix it for any. Okay, so this is going to be the case. So PA is true, and the other one is for any given integer k greater than or equal to the A. Okay, if pk is true, then pk plus 1, this is your job, is also true. Is also true. So you have to assume one of them as we did it and prove the next step is going to be true. Okay, equivalently, if you like, notation only, equivalently, this means pk implies, remember, implies pk plus 1. You remember when we put this conditionally with 2 lines, this means what? This is a tautology. This is true. So PA is true, is going to be basic step. The inductive space is if for any integer k, if pk is true, then you can prove pk plus 1 is also true. This is called inductive space. Inductive step. Basic step and the inductive step. Okay. If you can prove these two, okay. Yes, you have to assume that the pk is true, then prove pk plus 1 is true. You must assume this one, yes. You assume it's true, then your job is to prove the pk plus 1. Okay, so if we did these two, okay, suppose the two following statements are true. If this is going to be true, then we get by induction. So then by induction, if you like, by mathematical induction. Okay, mathematical induction. Pn Pn is true for all, okay, integers. And of course, bigger than or equal to what? A, the basic one. This is the procedure that we have to go through it. So first thing to do, you have to introduce the Pn. The problem, you see, what is the problem? You have to introduce the Pn. When you assume the precedent, two steps. Step one, you prove whatever you consider it's true for the basic step. That basic step is going to be the least number for the n that we're going to use, okay? That's a basic step. Then you fix a k. You fix a k and you assume that the pk is true. Okay, as we did it, you know, it was what, 8, 9, 10, 11, 12, that. You can go on forever, or assume one step is true, prove the next one. But you have to get the next one from the pk, because you need the pk to be able to form the pk plus 1. Mathematically, it's easy, because the difference is going to be just one term. But you have sometimes, you know, have a little bit of algebra. So if you can prove these two steps, you say, oh, by induction, you got it. By induction is the one that I talk about it. That's a piano theorem. That the natural number is going to be the only set that, okay, it's going to be the only set that satisfy this condition. So that's why automatically you say that, oh, it's true for all n. Any question? Okay, let's see how we're going to do it. Okay, what we are going to do, we can apply it, you know, in various places really. Let me stay with the numbers. We give you some equations to prove for us. Okay. In your book, they give you inequality. We can give you inequality, but the equation is more popular. You can use it for some other purposes. Theorem, I picked the divisibility. The divisibility is also nice. We pick these two and we practice on these because these are the ones they're going to use. Then there is another version, we call it a strong induction. It's the second one that you are going to use it more than the pure mathematicians in your case. Okay, so let's get an example to get the feeling, and then we can come back and again check it. Any questions so far? So it's a kind of a procedure. Let's see what is going to be really happen. But those money numbers, you see, money one is nice because we can see it, we can feel it. So I put a couple of them usually. There is one in your assignment, but I usually could. You have two in your next practice one. So we give you one because we want to know how you handle the real thing, if you like, okay? And the difficulty for this one is, as I've been doing this one for years, the way you write it down, you got to be very careful. Mathematically, logically, that's it. That's the best logic that you have. So you must be precise if you want to get 10 out of 10 out of this, okay? And after a while, you will get it. But don't rush, just follow the rules, okay? Nicely to give us the, it's like a machine. So we want to work machine. So you have to be everything in a proper place, okay? There you are. They give you some equation to prove. And this is the most famous one, okay? This is the one that probably have seen it in calculus. The identity that was proved by Gauss when he was 7 years old. Of course, he didn't use the mathematical induction. Okay, that's it. We want to prove this one. We simply ask you to prove by induction. Prove by induction. What do you want to prove? That famous, the sum of an integer, 1 plus 2, okay, plus 3, up to the n, is equal to n times n plus 1 over 2. You see, they give you the instruction for all n greater than or equal to 1. That's it. You want to prove this one. You know that if you may have seen it before, the way Gauss did it, he just write this backboard, if you like, 1 plus 2 plus 3 to the n, and he write n minus 1 to the 1. He add them together, all the numbers becomes n plus 1. So you are going to have n plus one number. So the total would be, let me just show you, but don't do it on the test because we ask you for the induction, okay? So maybe do it in calculus. You see 1 plus 2, this is the way he did it. And this is going to be, no, this is n minus 1, and the last one is n. So the way he did it, just write the numbers backward again, n plus minus 1. You just reduce it to the 2 and the 1. If you add these together, you see 1 and n would be n plus 1. N minus 1 and 2 would be n plus 1. So all of them would becomes n plus 1. Okay, n plus 1 and n plus 1. So you have n times n plus 1. So that would be n times n plus 1. But you did it twice. So that total one is going to be half of this. So that gives you n times n plus 1 over 2. That's a Gauss proof. But of course, we want to use mathematical induction. I'll show you so that you are not going to do it on the test. Okay, it's just one of those puzzles that people, when they talk about it, they say one, they fix it, of course, to the 100, 200. Okay, let's go back to the real proof. So a step by step, look at this one. You have to introduce the Pn first. Pn, predicate that you want to prove. Okay, this is one of the difficulty. I've seen the people, they don't introduce the Pn, but they go on. They talk about the Pn, you see. They talk about the Pn here. So I put the question mark. So where's your Pn? So make sure you introduce the Pn first. Pn is this identity that you want to prove. A property, remember the property. So you have to suppose this must be your opening statement. Suppose Pn is not equal to, it's just a statement. They estimated that the 1 plus 2 plus 3 up to the n is equal to n times n plus 1 over 2. This is Pn without this, quantifiers. That's a Pn. Property that you want to prove. So quickly you say, what do you want to prove? I should prove, 1 should prove, 1 should prove, 1 should prove that. So what do you want to prove? Pn is true. Pn is true for what? For all n greater than or equal to 1. That's the first step of your problem. You set up the Pn. Any question? Now we go to the step of the induction. Basic step and the inductive one. Any question? So make sure give us a Pn first. Okay, now the basic step, the B. Basic step, you have to prove that this is true for the basic value. The basic value is 1. Okay, basic value is 1. So this is how you start. We say, oh, if n is equal to 1. Okay, check the identity that you're going to get. You see, if you put n equal to 1 on both sides, what you have? This gives you only 1. So must be equal to what? 1 times 1 plus 1 over 2. So this would be 1 and 1 would be 2. That give you 2, 2. 2, 2 is equal to 1. That's it. So identity hold when n is equal to 1. So you can claim that the so P1 is true. That's the first part. That's true for the basic value. Look at this one. That the basic value, we call it A. So we should prove that the PA or the P1 in this case is true. That's step 1. Any question? Are you ready for the step 2? What are you going to do with the step 2? You have to fix it, you see. You have to fix the PK. So this is, are you done with this one? I want to go to the next page. So the inductive step. Fix the number first. So that's going to be inductive. Inductive. Fix it. Suppose Okay, that's going to be the next step. Suppose k greater than or equal to the basic value 1. K greater than or equal to the 1 is given such that pk is true. pk is true. pk is true. You have to prove that how we're going to get pk plus 1 from this one. So write it down. pk is true. What does it mean? This means, so write the identity. Identity is true for k. 1 plus 2 plus 3, okay, up to what? Up to k is equal to k times k plus 1 over 2. This is true. So what you want to prove, you have to show that you say if it's going to be adding the next step, next number. The next number is k plus 1. So your pk plus 1 would be 1 plus 2 plus 3, k plus 1. Then you have to prove this is true for k plus 1. Means if you replace the k by k plus 1, that gives you k plus 1 times k plus 2 over 2. This is what you have to prove. So what you do, basic part is going to be, so you write the rest. You write the pk plus 1. So this is true. We say, oh, note that. Add one more unit, one more term. 1 plus 2 plus 3 up to the k. Okay, and the next one. And plus k plus 1. Okay, k plus 1. This is what you have to find it. Okay, so you have to connect it to the given one, like the one we did before. So we want to evaluate this one. Look at this part. This part is given to you by the pk, if you like. So this would be equal to what? This would be equal to, okay, equal to 1, 2, 3 up to the k is already given. Substitute is equal to the k times k plus 1 over 2. Okay, plus what? Plus k plus 1. So you have to stay on the right. Stay on the right. Simplify this one to get what? K plus 1 times k plus 2 over 2. Algebra. Just common denominator will do it for you. So stay here. It's going to be equal to common denominator. Common denominator would be 2. So on the top you get the k times k plus 1 plus 2 times k plus 1. Don't rush to multiply it. You see, just check to see what you want. You see, there is a common factor here. Common factor out, that gives you k plus 1 times k plus 2 over 2. That's exactly what you want to prove. If you repeat this one, so you prove that the 1 plus 2 plus 3 up to what? Up to k plus 1 is equal to the k plus 1 times k plus 2 over, okay, over 2. And if you think about it, this is what? You see, this is pk plus 1. So you prove that the identity is true for k plus 1. You see, if it's a k, it's a k times k plus 1. If it's going to be k plus 1, it must be k plus 1 times k plus 2 over 2. So what you proved is, you proved that pk plus 1, so pk plus 1 is also true. Okay, so you assume that the pk is given to you, then you use it in order to prove that the pk plus 1 is true. Now we can claim that by induction, Pn is true always. Pn is going to be true for all n k then equal to the 1, and you're done. So it's very nice procedure, and it's not difficult to get. The idea is like you have to do something to the to the given one, because you have this one. You have to check what you want, pk, what's your pk plus 1. Pk plus 1 is the sum of the k plus 1 numbers. So you have to connect it to the previous one. Otherwise, you cannot do it. So what I did, I have up to the k plus 1. So this part over here is just, or I have it here, I substitute. You see, I substitute from the first part, k times k plus 1 over 2. Then, common denominator, give you the result right away. It's algebra involved, it's not going to be match. And so we prove that the basic step is true, P of 1 is true. And we assume that if pk is true, then we can do pk plus 1 for you for any k. So that's it. We just, by the piano principles, if you like, this can be done always. So this statement is true for all natural number n. Any question? So this is the way we write down. But on the test, you see this part here? The people, they made a mess over here. The way they write it down, they don't give me anything here, anything. So they start writing this one. You see this one? Doesn't make sense if you don't connect them together. You see, this maybe it's an identity. It's an equation. So what I did, this is k plus 1, I just substitute. I substitute, you have to work on this one to prove that this is going to be the same thing and the, okay, as the previous one. Then you'll be able, you'll be able to get the result. Okay, any question? So we have to practice. Give you another one. Any question on this one? Okay, let's give another one. And this next one is very popular. There is a formula for it. Of course, we are not going to use it. You know that in arithmetic, in college algebra, you have something, we call it a geometric sum or geometric series. So there is a formula that they use, even it's in your book, but we won't use induction to get these type of numbers, okay? There are a variety of this problem in your assignment, but all of them are the same. So I give you one of them so that you get used to them, okay? You know that if you get a fixed number and multiply by fixed numbers again, you can start with the 1, you multiply by 5. 5, okay, 5, 25, 125, 625. This is going to be a geometric sum. There is a common ratio, we call it the 5, and there is a formula that you can find the sum of these, these expressions. But we want to use induction to prove it. Okay, so this example will help you quite a lot. You have 3 problems in your assignment of this format. Let's see. We want again to prove by induction. Prove by induction. Is the sum of powers of any number. I give you 4 the numbers, but you can change it to the 5, to the 6. In that assignment, it's just the base is different. 4 cubed, 4 to the 4th, okay, 4 to the 5th, and we continue. Up to the 4 to the n. Something we call it geometric sum. And they claim that this is going to be equal to 4 times 4 to the n minus 16 over 3. We want to prove this is true always for n greater than or equal to 3. Very famous identity. Remember, no algebra, induction. Look at this pattern. This was all 4, this is 4. And you have the 4 to the n minus 4 squared, which is 16. And over here is like 4 minus 1, which is 3. There is a formula in. The formula is, I think it's a times r to the n minus 1 over r minus 1. It's in your book, but we don't need it. So if this is 5, it's going to be 5, 5, 5, 5. You get a 5 times 5 to the n. Of course, that would be given to you. 5 times 5 to the n minus 25. Minus 25 over 5 minus 1, which is 4. In your assignment, it's 7. If it's going to be 7, so that gives us 7 times 7 to the n minus 7 squared is 49 over 6. So it is the various problems that you can have. There is a little bit of algebra involved. Some people are not happy about it, so that's why we like this one. Okay, are you ready? Step one, the problem. What's a Pn? Okay, so nicely form the Pn. That's it. This is going to be our solution. So tell us what do you mean by the Pn? Suppose Pn is just this identity. Pn is the fact that the 4 cube, 4 to the 4th, 4 to the 5th, plus 4 to the n. Okay, and that's it. It's equal to the 4 times 4 to the n minus 16 over 3. No quantifier, remember. This is Pn, a statement that you want to prove. So what do you want to prove? You want to prove that one should prove, or I should prove? One should prove that Pn is true. Pn is true for all n, you see, for all n greater than or equal to 3. You see the basic number. You see the basic numbers would be different at different problem. Depends on the, sometimes you have a restriction, so you have to follow your restriction. Any question? There you are. We set up the problem. Go for it. Step one, basic step. Check to see basic step, basic value is 3. So we have to check to see if this identity is true when n is equal to 3, okay? And n equal to 3, you get 4 cube only. So this is it, basic step. Check if n is equal to 3. So what is your identity would look like? N equal to 3, that gives you 4 cube only. And you substitute here, it's going to be 4 times 4 cubed minus 16 over 3. You have to prove that both of them are the same. 4 cubed would be 64. So stay to the right. So this is going to be 4. That would be 64 minus 16 over 3. Okay, 64 minus 16 would be 48. So that gives 4 times 48 divided by 3. You simplify this one by 3, 48 by 3, that gives 16. 16 times 4 would be 64. Sorry, 60, yes, 64. And 64 is 4 cubed. Okay, which is a 4 cubed if you like. So 4 cubed equal to the 4 cubed. And the conclusion is P3 is true. So you proved it for the basic step. Any question? So that's the way you do it, you know, for the basic step. You go to the identity, whatever you have, and you show that, you know, the statement is going to be true for your basic values. Okay, so that's basic one. Now inductive case. Inductive case, you have to fix this one for k. You assume that this is true for k. So for k means you up to the 4 to the k. Then you have to prove the k plus 1, which is going to be up to the 4 to the k plus 1. That would be true, okay? So again, you're nicely writing down. Okay, so that was the basic one. This is going to be the inductive part. Inductive part, fix it. The fixing one would be, suppose. Okay, we suppose that this is going to be true for k greater than or equal to the basic value is 3. Okay, suppose that k bigger than or equal to 3 is given. Is given such that pk is true. You have to assume that this is going to be true, you know, so that you have something. Okay, so that you have something to work on it, if you like. Now write your pk plus 1. So what does it mean? So pk plus 1 means this identity, 4 cubed 4 to the 4 up to the 4 to the k is equal to, so this means your identity is going to be true when you put n equal to k. So it's going to be, it was what? It's a 4 times 4 to the k minus 16 over 3. Okay? So what you have to prove is, you say if it's end up with the k, so that would be 4 times 4 to the k minus 16 over 3. You want to prove this one for pk plus 1. So you have to add one more 4 to the k plus 1 to make it into the, okay, make it to the 4 to the k plus 1. Then you have to prove it's equal to the 4 times 4 to the k plus 1 minus 16 over 3. Okay, if you can prove it. So in that case, you did it for the k plus 1, okay? So let's form that one to see what's going to be you needed. Say, oh, note that what I want is this. I have the 4q, 4 to the 4, up to the 4 to the k. Okay, so I add the new part. So this is what I've already have. So plus 4 to the k plus 1. Because in order to go to the pk plus 1, you have to write it down up to the pk plus 1. So we can group them together. If you group them together, this would be what? This would be your pk. And you already got the pk. Okay, so you substitute, so it's going to be equal to, you substitute for this one because this is the k by induction you have it, it's going to be 4 times 4 to the k minus 16 over 3. Okay, and the leftover plus 4 to the k plus 1. Any question? We just substitute. Now you have to stay to the right, as I told you. You stay to the right, do the algebra and prove what? You have to prove that this is equal to the 4 times 4 to the k plus 1 minus 16 over 3. Okay, carefully find the common denominator would be 3. So it's going to be the result. That's the common denominator. On the top is going to be 4 times 4 to the k minus 16 plus 3 times 4 to the k plus 1. Okay, you have to do a little work a little bit to be able to get it. Remember what you want. 4 times 4 to the k plus 1. Distribute this one. You know, it's just like in algebra. So it's going to be equal to, distribute it carefully. 4 times 4 to the k. Here is going to be 4 to the, we add the powers. This is k, this is 1. So that gives you 4 to the k plus 1. Okay, we all time together, you get the same base. So you add the powers, then minus 4 times 16 would be 64. Okay, and this one over here is just 3 times 4 to the k plus 1 over 3. Any question? Now you have to combine them together. You see, look at these two. You may call this one z. Okay, so this is z, but this is plus 3z. 1z and 3z would be 4z. Okay, you combine them together. So this is going to be equal to, so 1, 2, that gives you 4z, 4 times k plus 1. Okay, this is, if you like, this is 1 4 to the k plus 1, and this is 3 4k to the plus 1. 1 apple, 3 apples. So this would be 4 apples, okay? Minus 64. Any question? Over 3, what do you want? Remember, we check again. You want 4 times 4 to the k plus 1 minus 16. So how are we going to get it? We have to factor out the 4. If you factor out the 4, so that gives you 4 times 4k plus 1. And that gives you 16 over 3. You see? So what is the other side? It was 4 to the third, 4 to the fourth, up to the 4 to the k, and the 4 to the k plus 1. So you show that the formula is true for k plus 1. Okay, this is k plus 1. Okay, which is going to be pk plus 1. So pk plus 1 is also true. By induction, let's say everything is happy. By induction, Pn is true. Pn is true for all n. You have to write this, okay? Bigger than or equal to 3, and then you're done. Okay, this is again is all algebra, but sometimes this part, okay, for example, this one that I simplified, I have only 1k plus 1, then I have a 3k plus 1. So that make it to the 4k plus 1. Okay, it's like 1z, 3z. It's going to be 4z. Then you pull out it as a factor and you get it. Okay, I told you in your assignment, you have it 7. Okay, it's the same thing that we can, that we can use. That's it for today. We are done with the mathematical induction. There is you get 2-3 sections on this one. The other one that we're going to cover is, we give a couple of examples of the divisibility. There is a theorem by Fermat. We call it the Fermat little theorem, if you like. That's the one. It's about the prime numbers, but you get divisibility. That's nice to work with these formulas. So we give that one and we finish the mathematical induction part 1. This ordinary induction, but there is another, we call it a strong one. Let's see how far we can go. We are eventually would like to get all of them by the end of the week. Okay, so study this one carefully, really. Okay, if you have any question, come back and we can discuss it again, because that's it. It's one of those things that you have to know it. And as I told you, we give you on the final all the question of this chapter 5 would be repeated on your final as well. So now make sure you get it, and it's very useful for your field, very useful. That's it. Any question? So see you on Wednesday, and I promise you that I do get reading one by the Wednesday. I have such big group of calculus. Like eventually I did it. I have 110 students and 11 questions, and it was quite a lot. But I'll do yours, and then so we can have a good idea of what we have done so far. Okay, so read it carefully. Again, we continue with this introduction. We are not going to hurry, because as we're done with this chapter, the rest are going to be straightforward. But we like to enjoy this one and get it through it. Really, it's quite interesting concept. Okay, that's it. Any questions? See you on Wednesday. Take care. Bye bye.
Thank you. See you Wednesday.
Thanks, Professor.